On a clear night in the southern sky, two of the brightest points you can see are not really two stars at all. They are the closest sun to our own, 4.37 light-years away, near enough that astronomers have already found planets around it and spoken openly of sending something there. Alpha Centauri feels like the one star within reach, the first stop on any map of where we might go, and the more carefully you look at what reaching it would take, the further away it begins to drift. The nearest star to the Sun may also be a door that stays closed to us, held shut not by anything hidden, but by distance, time, and energy on a scale the human story has never once crossed. Tonight, slowly and from the beginning, we're going to walk the whole length of that gap. On a clear night well south of the equator, two bright points sit low together near the long axis of the Southern Cross. To the naked eye, they look like one steady star, one of the brightest in the whole sky. That single point is really a pair, two suns bound to each other, and together they carry the name Alpha Centauri. They are the closest stars to our own. When sailors in the southern oceans used the two bright stars beside the cross as pointers, they were already looking, without knowing it, at our nearest neighbour in the galaxy. The brighter of the pointers is Alpha Centauri. The other is a star called Hadar, also known as Beta Centauri, and it sits far behind, hundreds of light-years away, only happening to line up near Alpha in our sky. That difference matters. Two stars can look like neighbours and be nowhere near each other. Alpha Centauri is genuinely close. Hadar only looks close. Almost everything about reaching across space begins with sorting the truly near from the merely apparent, and the southern pointers hold both kinds side by side. Alpha Centauri sits at a distance of 4.37 light-years. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers every second. Light is the fastest thing there is, and it still takes more than 4 years to cross from Alpha Centauri to us. So the light entering your eye on that southern night left those stars more than 4 years ago. You're seeing them not as they are, but as they were, which is true of every star, and truer of the near ones in a way you can almost feel. For most of human history, nobody knew which star was nearest. The sky looked flat, a dome of fixed lights, with no depth to it at all. The stars gave no obvious sign of how far each one stood. A faint star might be small and near, or huge and unthinkably far. Without a way to measure depth, the question of the nearest star had no answer. It took a specific method applied to specific stars before anyone could point and say with confidence that this one, and not that one, was closest to the Sun. That method, once it arrived, settled on the southern pair. Alpha Centauri turned out to be the nearest bright star, hanging just over 4 light-years away, closer than any other star you can easily see. From that fact, a quiet idea follows. If we are ever going to send something to another star, this is the one we would aim at first. It is the front door of the galaxy, the shortest possible step beyond the Sun. And yet the more you study that step, the stranger it becomes. 4 light-years sounds like a number you could plan around. It is not. It is a gap so wide that the fastest machines we have ever built would take tens of thousands of years to cross it. The nearness of Alpha Centauri is real, and it is also a kind of trap, close enough to tempt us and far enough to defeat us. So we begin with the simple fact and let it grow heavy. Alpha Centauri is the nearest star, a double sun low in the southern sky, 4.37 light-years away. Everything that follows is an attempt to take that one short line on a map and turn it into a real journey, and to watch, step by step, how a thing that looks within reach slips quietly out of it. Look more closely at that single bright point and it splits in two. The brighter half is called Alpha Centauri A, a star almost a twin of our Sun, a little larger, a little more luminous, burning the same steady yellow-white. Beside it sits Alpha Centauri B, smaller and cooler, an orange star with a touch less mass than the Sun. These two circle each other like partners in a slow dance, bound by gravity and to almost every telescope before the modern age they blurred into one. The dance between A and B is wide and unhurried. They swing around their shared centre of gravity once about every 80 years, drawing closer and then farther in a long ellipse. At their nearest, they come about as close as the Sun is to the planet Saturn. At their farthest, they stand as far apart as the Sun is from a point well beyond Neptune. So this is not a tight, frantic pairing. It is two ordinary stars keeping a stately, century-spanning rhythm, near enough to hold each other yet far enough that planets could, in principle, find stable room between them. Then there is the third member, and it changes the whole picture. Far out from the bright pair, more than 10,000 times the Earth-Sun distance away, drifts a small dim red star called Proxima Centauri. It is a red dwarf, the most common kind of star in the galaxy, and one of the faintest, so dim that you cannot see it without a telescope despite its nearness. Proxima is loosely bound to A and B, looping around the pair over a span that may run to hundreds of thousands of years. 3 stars, then, share this one system, 2 close and bright, 1 distant and faint. The name Proxima means nearest, and the name is honest. Of these 3 stars, Proxima sits slightly closer to us than A and B do, by a small but real margin. So when people speak of the nearest star to the Sun, they're usually speaking of Proxima Centauri, the dim outrider of the bright pair, the one no unaided eye has ever caught. The closest star to Earth, other than the Sun itself, is a star you have never seen and never will without help. It is worth holding all 3 together in your mind because the system is a small portrait of a hard truth. Alpha Centauri A is the familiar one, sun-like and warm, the star you would picture if you imagined a second home. Alpha Centauri B is its quieter companion. Proxima is the strange, faint, flaring red one that happens to be nearest, and it is also the one around which the first planets were found. The closest, the most sun-like, and the most planet-bearing are not the same star, and that small split runs through everything that follows. For now, the shape is enough. 1 point of light in the southern sky resolves into a family of 3. 2 yellow and orange suns waltz across 80 years, while a faint red ember circles them from a great distance, taking ages to complete a single loop. All 3 lie just over 4 light-years away, closer to us than anything else in the night. They move together, bound across distances that dwarf our entire solar system, and they are still, by the measure of the galaxy, right next door. 4 light-years is a phrase that slides past easily, and that is the danger in it. The mind hears a small whole number and files it beside other small numbers, a 4-hour drive, a 4-day trip. So it helps to slow down and build the distance out of things the body actually knows, because only then does the gap to Alpha Centauri start to feel like what it is. Begin with the Sun. Light from the Sun reaches your face in about 8 minutes. That light has crossed 150 million kilometers to get to you, the full width of Earth's orbit, in the time it takes to boil an egg. The Sun is, by the standards of the night sky, absurdly close, and even so its light spends 8 minutes on the road. The whole of our daytime sky is lit by a star 8 light-minutes away. Now push outward to the edge of the planets. Light from the Sun takes about 4 hours to reach Neptune, the most distant major planet, far out on the cold rim of the Sun's family. 4 hours, just across our own solar system. The spacecraft Voyager 1, launched in 1977, and now the most distant human-made object, has been flying outward for almost 50 years. It has travelled a little over 20 light-hours from home, not light-years, light-hours. After half a century at more than 60,000 kilometers an hour, Voyager 1 has covered less than a single day at the speed of light. Hold that beside Alpha Centauri. Its light takes 4.37 years to reach us. Not minutes, not hours, but years, more than 4 of them. To turn Voyager's 20 light-hours into Alpha Centauri's 4+ light-years, you would have to multiply the distance by something close to 2,000. The single farthest thing we have ever flung from Earth after 50 years of travel, has crossed less than 1,000th of the way to the nearest star, and it is not even pointed there. There is a smaller, sharper way to feel it. Imagine you could shrink the entire Earth-Sun distance, those 150 million kilometers, down to a single step, one normal stride of your foot. At that scale, Neptune would be about 30 steps away, a short walk across a room, and Alpha Centauri, on that same map where the Sun and Earth are one stride apart, would be over 270,000 steps away. You could walk the length of the solar system in less than a minute, and then you would have to keep walking step after step for the better part of 100 miles to reach the nearest star. This is the quiet shock under the small number. Within the solar system, distances are vast but crossable. We have sent machines to every planet, landed on a comet, touched the edge of the Sun. The jump to Alpha Centauri is not the next rung on that ladder. It is a different kind of distance, a 1,000-fold leap past the farthest place we have ever reached, into a gap so wide that our boldest journeys so far do not even register as a first step. So when someone says Alpha Centauri is only 4 light-years away, the word only is doing something deceptive. The distance is small for a star, the smallest there is, and it is still enormous beyond ordinary use. Holding both of those at once, the nearness and the enormity, is the beginning of understanding why this nearest star may already lie beyond us. For thousands of years, the stars kept their distances secret. They looked like fixed points on a dark sphere, and no one could tell whether a star was near and faint or far and brilliant. The whole sky might have been a thin painted shell or a bottomless deep, and from the ground there was no way to choose. To find the nearest star, someone first had to find a way to measure the depth of the sky at all, and that turned out to be one of the hardest measurements in the history of science. The key is an effect you can feel with your own eyes. Hold up one finger at arm's length and look at it with one eye, then the other. The finger seems to jump against the far wall behind it. That apparent jump is parallax, and it happens because your two eyes look from slightly different positions. The nearer the finger, the bigger the jump. Move the finger close to your nose and it leaps wildly. Hold it far away and it barely shifts. Distance and the size of the jump are tied together, and if you can measure the jump, you can work out the distance. The Earth gives us 2 enormous eyes, 6 months apart. In summer, our planet sits on one side of its orbit around the Sun, and in winter on the far side, 290 million kilometers away. A nearby star, watched from those 2 opposite points, should shift its position very slightly against the far more distant stars behind it, just as your finger shifts against the wall. The catch is that even the nearest stars are so far away that the shift is almost unimaginably tiny, a hair's width wobble that defeated astronomers for centuries. The breakthrough came in the 1830s, and Alpha Centauri was at the heart of it. A Scottish astronomer named Thomas Henderson, working at the Cape of Good Hope at the southern tip of Africa, made careful measurements of Alpha Centauri's position over time. The southern station gave him a clear view of the bright pointer star. When he later worked through his numbers, he found a real parallax, a genuine seasonal shift, and from it a distance. He had measured, for the first time, how far away another star truly was. Henderson was cautious and slow to publish, and so the formal credit for the first stellar distance often goes to the German astronomer Friedrich Bessel, who in 1838 announced the distance to a faint star called 61 Cygni. The 2 results came within a year or so of each other, 2 careful people in 2 hemispheres finally reaching into the depth of the sky. Henderson's star, Alpha Centauri, turned out to be the closer of the 2, and indeed the closest bright star of all. That moment changed what the night sky was. It stopped being a flat ceiling and became a space with real depth, stars scattered through it at measurable distances, and it answered at last the old question of which star is nearest. The bright southern pointer, Alpha Centauri, sat closer than any other star anyone could plainly see, just over 4 light-years away, confirmed not by guesswork but by the slow seasonal wobble of its position as Earth swung around the Sun. So we know Alpha Centauri is closest the same way you know your finger is near your face. by watching it shift as you change your point of view. The method is humble, almost childlike, and it carries the entire weight of measuring the cosmos. Every map of where we might one day travel rests on that first patient measurement of a tiny stellar jump. Henderson measured the bright pair, and for a while it seemed the matter was settled, that Alpha Centauri A and B mark the nearest point in the sky. But the system held a quieter secret, a third star too faint to notice in the glare of the other two, and finding it shifted the title of nearest star onto a point of light no one had ever seen by eye. The discovery came in 1915 from a Scottish-born astronomer named Robert Innes, working at the Union Observatory in Johannesburg in South Africa. Innes was studying stars that share the same motion across the sky, a sign that they may belong together. He noticed a very dim red star moving across the heavens in step with Alpha Centauri, keeping pace with the bright pair as they drifted year by year. Stars that move together usually travel together, bound by gravity or born from the same cloud. This faint companion was clearly tied to the famous pair. Innes worked out that this dim star lay slightly nearer to us than Alpha Centauri A and B, and so he gave it the name Proxima, from the Latin for nearest. Proxima Centauri, the nearest star. Later, more precise measurements confirmed it. By a margin of a few hundredths of a light year, small but real, Proxima sits closer to the Sun than its bright siblings. It holds the record. Of all the stars in the sky, this is the one whose light reaches us across the shortest distance, just over 4.2 light-years. What makes the fact strange is what Proxima is. It is a red dwarf, a small, cool, deeply dim star, with only about an eighth of the Sun's mass and a tiny fraction of its brightness. It is so faint that across that short distance it cannot be seen without a telescope. The nearest star to our Sun is invisible to the naked eye, drowned out by countless more distant stars that merely shine brighter. Brightness in our sky, it turns out, is a poor guide to nearness. Red dwarfs like Proxima are not rare oddities. They are the most common kind of star in the galaxy, outnumbering Sun-like stars many times over. Most of the stars around us are these small, dim, long-lived embers, burning their fuel so slowly that they can shine steadily for trillions of years, far longer than the Sun will last. The galaxy is, in truth, a place mostly lit by faint red stars, and we miss this because our eyes are drawn to the rare bright ones. Proxima is a close, clear example of the true majority. So the nearest star is not the warm, sun-like one we might have hoped for. It is a small red dwarf, dim and cool, that no human eye ever caught until a telescope and a patient study of motion revealed it. The familiar bright pointer in the southern sky is real and close, but the actual record holder hides just beyond it, a faint ember keeping pace with the brighter two. This matters for everything that comes next, because Proxima is where the first planets were found, and Proxima is the most natural target for any probe aimed at the nearest star. We would not be sailing toward a calm yellow twin of the Sun. We would be sailing toward a tiny, cool, restless red dwarf, the most common and most overlooked kind of star there is, the true nearest light in the whole of the night. For a long time, the stars beyond the Sun were just points of light, and no one knew whether any of them held planets at all. That changed in the 1990s, when astronomers began finding worlds around other stars, and it changed again, far closer to home, in the year 2016, when a planet was confirmed orbiting the nearest star of all. Around faint red Proxima Centauri, there was a world. The planet is called Proxima b. It was found by a team using telescopes of the European Southern Observatory in Chile, watching for a subtle clue. A planet does not just orbit its star, it tugs on it, and the star wobbles very slightly in response, swinging toward us and away as the unseen planet circles. That tiny back and forth motion shows up as a rhythmic shift in the star's light, and from it astronomers can infer a planet's presence and rough mass. Proxima b revealed itself through exactly this gentle stellar wobble, a small world betraying itself by the pull it exerts. Proxima b is roughly the mass of the Earth, perhaps a little heavier, a rocky world rather than a ball of gas. And it sits in an interesting place. It lies within what astronomers call the habitable zone, the band of distances from a star where the temperature could allow liquid water to pool on a surface. Too close, and water boils away. Too far, and it freezes solid. Proxima b orbits within that narrow temperate band, which is why its discovery stirred such excitement. The nearest star has an Earth-sized planet at a distance where water might, in principle, stay liquid. There is a catch hidden in that promise, and it comes from the kind of star Proxima is. Because Proxima is so dim and cool, its habitable zone lies very close in, far nearer than Earth is to the Sun. Proxima b completes a full orbit in only about 11 days. A year on that world is shorter than 2 of our weeks. It huddles close to the faint red ember that warms it, and that closeness brings problems we will come back to. Problems with flares, and with the way such a near orbit can lock a planet's face toward its star. Proxima b is not alone. Further study has pointed to at least 1 and possibly 2 more worlds around the same star. There are signs of a planet called Proxima c, a heavier world on a much wider orbit, far out in the cold where it takes years to circle once. And there are hints of a small, close-in world sometimes called Proxima d, lighter than Earth, hugging the star even tighter than Proxima b. The nearest star, it seems, carries a small family of planets, near and far, large and small, so the picture sharpens. The closest star to the Sun is not a barren point of light, but a system with worlds, including one rocky planet about the size of Earth, sitting in the temperate band where liquid water is at least conceivable. If you wanted a reason to look hard at the nearest star and dream of going there, this is it. The target is not just close, it has ground to stand on, and a slim chance of water, and a place in our imagination that few other stars can match. That is what makes the rest of this story so difficult. We have found, right next door by cosmic standards, an Earth-sized world in the habitable zone of the nearest star. The destination is real, named, and mapped. And still, as we'll see, simply getting a single small machine to fly past it lies at the very edge of what we can imagine doing. Put the pieces together, and you can see why Alpha Centauri has become the obvious dream, the star that every serious plan for interstellar travel returns to first. It is not chosen at random or for romance. It is chosen because by almost every measure that matters for a first attempt, it is the easiest possible target, the lowest branch on a very high tree. Start with the plain fact of distance. Alpha Centauri is the nearest star system to the Sun, just over 4 light-years away. Every other star is farther, most of them far farther. If you are going to attempt the hardest journey ever conceived, you naturally pick the shortest version of it. The nearest star is the shortest interstellar trip there is, and there is no closer one to fall back on. This is as near as another star will ever be. Then there is the kind of stars it holds. Alpha Centauri A is remarkably Sun-like, a near twin of our own star in size, colour and warmth. Alpha Centauri B is a steady orange companion, also a calm, long-burning star. A system with a Sun-like star feels familiar, even hospitable, the sort of place where the physics of light and warmth would resemble what life on Earth already knows. The nearest star is also one of the most Sun-like neighbours we have, which doubles its pull on the imagination. Add the planets. Around Proxima, the system's faint third star, sits Proxima b, a roughly Earth-sized world in the habitable zone, where liquid water is at least possible. A target with a planet is far more compelling than a bare star, because a planet is a place, a surface, a world that could be studied, photographed, perhaps one day touched. The nearest star does not just offer a destination in space, it offers a world to aim at, already found, already named. So the case builds on itself, closest of all stars. Home to a near twin of the Sun, orbited by an Earth-sized planet in the temperate zone. If you were designing from scratch the single most tempting first destination beyond the solar system, you would struggle to improve on what Alpha Centauri already is. It is as though the galaxy placed its most inviting sample right at our doorstep, as near as such a thing can be. This is why nearly every interstellar study, from quiet thought experiments to funded research projects, points its arrow at Alpha Centauri. When engineers imagine a starship, this is where they send it. When scientists sketch a probe, this is the system on the page. It is the natural first step, the proving ground, the place humanity would go before anywhere else, simply because everywhere else is harder in every way. And that is exactly what makes the difficulty so striking. This is the easy one. This is the nearest, the most sun-like, the best equipped with worlds, the most favourable target the sky has to offer. If reaching Alpha Centauri turns out to lie at the very limit of the possible, or just beyond it, then the rest of the galaxy is harder still by a wide margin. The front door is the lowest, gentlest step we will ever face. So we hold this clearly before going further. Alpha Centauri is not a distant long shot among many. It is the chosen one, the obvious and best first target, picked for sober reasons. Everything that makes it look reachable is real, and the journey ahead is the story of how, even for this nearest and friendliest of stars, the gap may already be too wide for us to cross. To feel how wide that gap really is, we have to set a fair ceiling on human speed, and that means looking at the fastest things we've ever actually built and flown. Not the speeds we dream about, but the ones already achieved, out in real space, by real machines. Two objects mark that ceiling, one heading outward forever and one diving sunward, and together they show how fast humanity can presently move. The first is Voyager 1, launched in 1977, and now the most distant human-made object in existence. After flying past Jupiter and Saturn, it was thrown outward by their gravity and has been coasting away from the Sun ever since. It now travels at about 61,000 kilometers an hour relative to the Sun, roughly 17 kilometers every second. That is fast enough to cross the entire United States in about 4 minutes. Voyager 1 is the farthest and one of the fastest things our species has ever sent into the dark, and it has been moving for nearly 50 years. The second is the Parker Solar Probe, a very different kind of record holder. Launched in 2018, it was built to dive again and again toward the Sun, skimming closer than any spacecraft before it. As it falls inward, the Sun's immense gravity whips it to astonishing speed. At its fastest approach, it reaches around 690,000 kilometers an hour, close to 200 kilometers every second. That makes the Parker Solar Probe the fastest human-made object ever, by a wide margin, a machine that crosses in 1 second a distance Voyager covers in 12. These two represent the honest extremes of what we have done. Voyager is the fastest thing on a path that actually leaves the solar system, drifting out toward the stars on its own. Parker is the fastest thing overall, but it earns its speed by falling toward the Sun, not by heading out between the stars, and most of that speed is borrowed from solar gravity at closest approach. One shows our best outbound cruise, the other shows our highest possible velocity, achieved under the most favourable possible push. It helps to sit with how hard won even these speeds are. Voyager's velocity took the gravity of giant planets to build. Parker's took the pull of the Sun itself and a spacecraft engineered to survive a furnace. These are not casual numbers. They are the summit of 70 years of spaceflight, the result of our finest rockets, our cleverest trajectories, and the gravity of the largest bodies in the solar system pressed into service. There is no faster machine in the human record than these, and yet, for the journey to Alpha Centauri, even these turn out to be slow almost beyond belief. The Parker Solar Probe's 200 kilometers a second sounds tremendous, and against everyday life it is. Against the gap to the nearest star it nearly vanishes. The distance is so vast that our fastest object, flying flat out, would still need a span of time that dwarfs all of recorded history to make the crossing, and that is the figure we turn to next. So the ceiling is set, honestly, and with real machines. Voyager 1 at 17 kilometers a second, drifting outward for half a century. The Parker Solar Probe at nearly 200 kilometers a second, the swiftest thing we have ever made. These are the true limits of human speed as it stands today, the fastest we have ever moved anything, and they are the numbers we will now carry across 4 light years to see what time they demand. Take our fastest machines then, and point them at Alpha Centauri. Hold their speed steady and let them fly straight for the nearest star. The distance is fixed at just over 4 light years. The speeds are real, already achieved. All that is left is to divide one by the other and read the time. The answer is where the dream meets the wall. Begin with Voyager 1, our fastest outbound craft, drifting at about 17 kilometers a second. If Voyager 1 were aimed directly at Alpha Centauri, which it is not, it would need roughly 70,000 years to arrive. 70,000 years. To grasp that, look backward instead of forward. 70,000 years ago, our ancestors were still spreading out of Africa, living in small bands of hunter-gatherers, long before farming, before writing, before the first city. A Voyager launched at the dawn of the modern human story would only now be approaching the nearest star. The Parker Solar Probe, our outright speed champion, does better, but not nearly enough. At its blistering 200 kilometers a second, if it could somehow hold that speed all the way, the trip would still take on the order of 6,500 years. And that is wildly generous, because Parker only reaches that speed for brief moments at the bottom of its dive toward the sun. It cannot hold it, but grant it anyway. 6,500 years is still longer than all of recorded history. The first written words are about 5,000 years old. A probe leaving today at Parker's peak speed would arrive in a future as far ahead of us as the invention of writing lies behind us. This is the tyranny of time, and it is the hard heart of the whole problem. The issue is not that we cannot build fast machines. We can, and we have. The issue is that the distance is so enormous that even our fastest machines turn it into a journey of thousands or tens of thousands of years. No crew could live that long. No mission could be planned across such a span. No institution on Earth has ever lasted even a fraction of it. The gap simply swallows any human timescale whole. It is worth saying plainly what this rules out. A trip of tens of thousands of years is not a voyage anyone could undertake and return from. It is not even a voyage that the civilization launching it could expect to still exist to receive. Whole languages rise and vanish in such a span. Empires that seemed eternal leave only ruins. To send Voyager to Alpha Centauri at its own speed is to launch a message in a bottle toward a shore that may have no one left who remembers throwing it. And notice that we have not yet reached any exotic limit. We have not run into the speed of light or the strangeness of physics near it. We are nowhere close. Our fastest probe moves at less than 1,000th of light speed. The wall we have hit is far more ordinary and far more stubborn. It is simply that the distance is vast and our speeds are small, and the time that falls out of dividing the one by the other is longer than human things endure. So the first hard truth of reaching the nearest star is not about exotic engines or unknown physics. It is arithmetic, plain and merciless. Our best speed, our nearest target, and the time still runs to thousands of years. To cross this gap in any span a person could live to see, we would need to go vastly, almost unimaginably faster. And the next question is whether the rocket, the only tool we have ever used to move through space, can take us there. If the trouble is that we're too slow, the obvious answer is to go faster, and to go faster we reach for the rocket, the only machine that has ever carried us off the Earth. But the rocket carries a hidden flaw that becomes ruinous over interstellar distances, and that flaw was written down more than a century ago in a single elegant equation. It is the deepest reason the gap to Alpha Centauri resists us. The man who wrote it was Konstantin Tsiolkovsky, a nearly deaf Russian schoolteacher working alone in the 1890s and early 1900s, decades before any rocket reached space. Tsiolkovsky worked out, on paper, the basic mathematics of how a rocket moves, and his result is now called the Tsiolkovsky rocket equation. It is the foundation of all spaceflight, and it contains both the promise of the rocket and the trap inside it. The idea behind a rocket is simple. It throws mass backward, and by reaction it is pushed forward, the way a swimmer pushes off a wall, or a person on ice is shoved back when they throw a heavy ball. To go faster, a rocket must throw its propellant out the back as fast as it can, and throw a great deal of it. Speed comes from how fast you can expel your exhaust, and how much of your ship is fuel. So far, so reasonable. The trouble hides in that second part, in how much fuel. Here is the trap. To reach a higher final speed, a rocket needs more propellant, but that propellant has mass, and it must itself be carried and accelerated by the rocket, which means you need still more propellant to push the propellant you already added. To push that extra fuel, you need yet more fuel again. The amounts do not grow gently, they grow exponentially. Each increase in target speed multiplies the fuel required, and past a certain point the numbers explode toward the impossible. The rocket equation makes this exact. The relationship between the speed you want and the fuel you must carry is not a straight line, but a steep, accelerating curve. Doubling your goal does not double your fuel, it can multiply it many times over. To reach modest speeds within the solar system, the fuel demands are already large, which is why a rocket on the launch pad is mostly propellant wrapped around a tiny payload. To reach the speeds needed for the stars, the same math turns monstrous. Push the equation toward interstellar velocities and it breaks against reality. To send even a small ship to Alpha Centauri in a human lifetime using ordinary rocket fuel, the equation demands a quantity of propellant so vast it would outweigh planets, more fuel than exists in any form we could gather. The ship to push the fuel, to push the fuel, to push the fuel piles up, until the answer is a number with no physical meaning. The rocket, our one proven tool, defeats itself the moment we ask it to cross between stars. This is the equation that will not bend. It is not a limit of our engineering skill or our budgets. It is built into the very logic of throwing mass to move, written into the nature of rockets themselves. Tsiolkovsky saw it clearly over 100 years ago, and nothing since has softened it. To reach the nearest star, we cannot simply build a bigger rocket of the usual kind. The usual kind, scaled up, collapses under its own fuel, and that hard fact forces every serious plan to look for some other way entirely. The rocket equation does not care how clever the chemistry is, but it does care about one number above all, and that number is how fast the exhaust leaves the engine. Chemical rockets, the kind that lift every satellite and every astronaut, are limited in that number by the chemistry itself, and that limit is exactly why the chemical rocket is the wrong tool for the gap to Alpha Centauri. A chemical rocket works by burning fuel and oxidizer together, hydrogen and oxygen, or kerosene and oxygen, releasing the energy stored in their chemical bonds. That energy heats the exhaust gas and blasts it out the back at high speed. The best chemical engines fling their exhaust out at around 4 to 4.5 kilometers a second. That is genuinely fast, faster than a rifle bullet, and it is enough to reach orbit, the moon, and the planets. Within the solar system, chemical rockets have taken us everywhere we have gone. But 4.5 kilometers a second is a hard ceiling for chemistry, set by how much energy the bonds between atoms can hold. You cannot simply demand a hotter, faster exhaust from chemical fuels. The energy locked in those bonds is fixed by nature, and it caps the exhaust speed near that few kilometers a second mark no matter how the engine is designed. The chemical rocket is already near the best it can ever do, and that best is far short of what the stars require. Feed that ceiling into the rocket equation, and the result is bleak. To reach even a small fraction of the speed of light with a chemical rocket, the equation calls for a fuel-to-ship ratio so large it defies belief. The mass of propellant needed would dwarf not just the spacecraft, but, in the most demanding versions, quantities of matter far beyond anything we could ever assemble. The exponential curve, fed by such a slow exhaust, climbs into numbers that have no home in the real universe. Chemistry simply cannot push hard enough, fast enough, to win against that distance. There is a clean way to see why. The exhaust speed sets the natural scale of speeds a rocket can comfortably reach. A rocket strains to go much faster than its own exhaust without burning fuel in absurd amounts. A chemical rocket's exhaust moves at a few kilometers a second, so a few kilometers a second is its comfortable range, with great effort stretching it to 10 or 20. The journey to Alpha Centauri in a human lifetime needs speeds measured in tens of thousands of kilometers a second, thousands of times beyond that natural scale. The mismatch is not small, it is a chasm. So the chemical rocket, for all its triumphs, is simply the wrong instrument for this task, the way a rowboat is the wrong vessel for crossing an ocean in an afternoon. It is not that the rowboat is badly made, it is that the scale of the journey is wholly beyond what that tool was ever shaped to do. Chemistry got us off the planet and across the solar system, and there its reach ends. The stars demand a different source of energy altogether, something that can throw exhaust not at kilometers a second, but at a meaningful fraction of light itself. That realization is where the real search begins. Once you accept that ordinary rockets cannot make the crossing, you start hunting for engines that draw on deeper, fiercer sources of energy, the splitting and fusing of atomic nuclei, the annihilation of matter and antimatter, or no onboard fuel at all but a push from outside. Each of these has been seriously studied, and each opens a door while raising new walls, and it is to those harder, stranger engines that the story of reaching Alpha Centauri now turns. If chemical fuel is too weak, the next idea is to reach for the most violent energy humanity has ever unleashed, and to use it not to destroy, but to travel. In the 1950s, a group of brilliant physicists proposed exactly that. Their plan was to drive a spaceship by setting off a long string of nuclear explosions behind it, riding the blasts outward like a surfer riding a series of waves. The project was called Orion, and it is one of the strangest serious ideas in the history of spaceflight. The concept came from minds including the physicists Stanislaw Ulam and Frederick de Hoffman, and the project was led in part by Ted Taylor, a weapons designer, and the renowned physicist Freeman Dyson. Their reasoning was blunt and bold. Nuclear bombs release staggering amounts of energy, far beyond any chemical fuel. If you could harness even a fraction of that energy to push a ship, you could reach speeds chemistry could never touch. So they designed a craft that would carry a magazine of small nuclear bombs and drop them out the back, one after another. The design was as direct as it sounds. Behind the ship sat a massive, thick metal plate, the pusher plate, mounted on giant shock absorbers. The ship would eject a nuclear bomb behind it and detonate it a short distance away. The blast would slam against the pusher plate, shoving the whole vehicle forward. Then another bomb, and another, perhaps one every second or few seconds, each explosion kicking the ship to higher speed. The shock absorbers would smooth the violent jolts into a steadier push for any crew aboard. This was nuclear pulse propulsion, travel by riding a chain of bombs. What makes Orion remarkable is that, on paper, it actually worked. The physics was sound. Unlike many Starship dreams, Orion did not depend on undiscovered science. It used bombs we already knew how to build and a plate we already knew how to forge. Studies suggested an Orion craft could reach speeds far beyond chemical rockets, and the most ambitious versions, loaded with enormous numbers of bombs, were imagined reaching a few % of the speed of light. For the first time, a journey to the nearest star moved from pure fantasy toward a sketchable, if monstrous, engineering plan. But Orion carried obvious and grave problems. To launch from Earth, it would detonate nuclear bombs in the atmosphere, scattering radioactive fallout across the sky. The environmental and political cost of that was unacceptable, and the signing of treaties banning nuclear explosions in the atmosphere and in space effectively ended any hope of building it. The very thing that gave Orion its power, the nuclear blast, also made it something the world could not allow to fly, at least not from the ground. So Project Orion remains a haunting what-if, a design that could plausibly have begun the journey to the stars and was set aside for sound and sobering reasons. It showed that the energy needed to approach interstellar speeds does exist within our reach, locked inside nuclear weapons, and that we had, in a sense, already built the fuel before we knew what else to do with it. It also showed the price. The forces required to cross to Alpha Centauri are the forces of the bomb, and learning to ride them without poisoning our own world, or ourselves, is its own enormous problem, one that the next generation of Starship designers tried to solve in a cleaner way. Orion was loud, dirty, and powered by fission, the splitting of heavy atoms. The next great Starship study tried for something cleaner and even more powerful, drawing on fusion, the joining of light atoms that powers the sun itself. In the 1970s, a group of engineers and scientists in Britain sat down to design, in real detail, a starship that could actually reach another star. They called it Daedalus, and it remains one of the most thorough interstellar designs ever attempted. Project Daedalus was the work of the British Interplanetary Society, a group of volunteers who met over several years to study the problem seriously. Their goal was strict. They wanted a ship that could reach a nearby star within a single human working lifetime, around 50 years, using physics that was understood or plausibly within reach. They did not aim for Alpha Centauri but for Barnard's star, another close star about 6 light-years away, which at the time was thought mistakenly to have planets. The principles, though, apply to any nearby target. Their design was enormous and driven by fusion. The ship would carry vast tanks of special fuel, including a rare form of helium called helium-3, and ignite tiny pellets of it in rapid succession with beams of electrons, a controlled chain of miniature fusion explosions. Each pellet would fuse and blast out the back, pushing the ship forward, hundreds of detonations every second. In effect, it was a refined cousin of Orion's idea, trading crude bombs for clean, tiny fusion bursts. Daedalus was designed to reach about 12% of the speed of light, fast enough to cross to Barnard's star in roughly 50 years. Daedalus was a flyby probe, not a ship that would stop. It would tear past its target star at a tremendous speed, taking what data it could in the brief hours of passage, with no way to slow down. It was also gigantic, far larger than anything ever launched, and it assumed industrial capabilities we do not have, including mining the helium-3 fuel from the atmosphere of Jupiter. It was a design meant to prove a point, that an interstellar probe was not forbidden by physics, rather than a blueprint to be built next year. Decades later, a new group revisited the idea in a study called Project Icarus, named as a deliberate knowing echo. Where Daedalus had been a first bold sketch, Icarus aimed to update and refine it with modern knowledge, re-examining the fusion engine, the fuel and the mission in light of all that had been learned since the 70s. Icarus, like Daedalus, was a study rather than a construction project, a way of keeping the hard questions alive and testing whether the dream had grown more or less plausible with time. What both projects assumed is the key to understanding them. They assumed enormous quantities of rare fusion fuel, gathered by industry on a scale spanning the whole solar system. They assumed fusion engines that work reliably for years, when controlled fusion for power on Earth has remained stubbornly out of reach for generations. They assumed a willingness to build something the size of a skyscraper and fling it into the dark on a 50-year one-way errand. None of these are forbidden by physics, and every one of them lies far beyond what we can do today. So Daedalus and Icarus mark an honest middle ground. They show that a fusion starship is not a contradiction, that the laws of nature permit a probe to reach a nearby star in decades. They also show how much that permission costs, in fuel, in scale, in capabilities we have imagined but never built. The fusion dream is real, and it is distant, and chasing it leads naturally to an even more extreme source of energy, the most concentrated fuel the universe allows. Push the search for energy to its absolute limit, and you arrive at antimatter, the most concentrated fuel the laws of physics permit. Nothing releases more energy for its mass. If fusion is the fire of the sun, antimatter is something fiercer still, and on paper it is the perfect Starship fuel. The trouble is that getting it, and keeping it, runs into walls so steep they may never come down. Antimatter is real, not science fiction. For every kind of ordinary particle, there exists a mirror image partner with opposite charge. The electron has its opposite, the positron. The proton has the antiproton. These antiparticles are made and studied in laboratories, most famously at CERN, the great physics centre near Geneva, where antiprotons and antiatoms have been created and briefly held. Antimatter is a known, measured part of nature, produced in tiny amounts by some of the most advanced machines ever built. What makes antimatter extraordinary is what happens when it meets ordinary matter. The two annihilate, vanishing completely and converting their entire mass into energy in a flash of pure radiation. This is the most efficient energy release known. Ordinary chemical fuel converts a vanishingly small fraction of its mass to energy. Nuclear fission and fusion do far better, converting a fraction of a percent. Matter-meeting antimatter converts essentially all of it. Gram for gram, antimatter holds the most energy any fuel could ever carry, which is exactly why Starship designers keep returning to it. A spacecraft powered by matter-antimatter annihilation could, in principle, reach a large fraction of the speed of light, turning the journey to Alpha Centauri into a trip of years or a few decades rather than millennia. The exhaust would scream out at a meaningful share of light speed, satisfying the rocket equation's hunger in a way no chemical or even fusion fuel can. In the pure mathematics of propulsion, antimatter is the answer the equation has been asking for all along. Then comes the wall. We can make antimatter, but only in unimaginably tiny quantities, a few atoms at a time, at staggering cost. All the antimatter ever produced by humanity, gathered together, would amount to a vanishingly small speck, nowhere near enough to lift a feather, let alone drive a starship. To fuel a real interstellar mission would require kilograms or tons of antimatter when we struggle to make billionths of a gram. Producing it at the needed scale would, by current methods, take longer than the age of the universe, and cost more than the wealth of the world many times over, and even if we could make it, we could barely hold it. Antimatter annihilates the instant it touches ordinary matter, so it cannot be kept in any normal container. It must be suspended in magnetic and electric traps, in a perfect vacuum, never allowed to touch a single wall, for the entire length of a years-long voyage. A momentary failure of those traps would release the stored energy all at once, in a catastrophe. Storing Starship quantities of antimatter safely is a problem we have no idea how to solve, so antimatter stands as the ultimate fuel and the ultimate frustration, the place where the energy is finally, in principle, enough, and the practical barriers become almost absolute. The physics says yes, this would work. The making and the keeping of it say no, not in any future we can presently see. Faced with that wall, some designers gave up on carrying fuel at all and asked a different question. What if the ship brought no engine fuel with it and was pushed instead from the outside by light? Every method so far has tried to carry the source of speed aboard the ship, and everyone has drowned in the cost of its own fuel. So a different idea took hold, one that leaves the heavy engine behind on Earth entirely. Instead of carrying fuel, the ship would carry almost nothing and be pushed from a distance by a beam of light. This is the principle behind Breakthrough Starshot, the most concrete interstellar plan of our time. Breakthrough Starshot was announced in 2016, backed by the investor Yuri Milner, and supported by figures including the physicist Stephen Hawking. It set itself a bold and specific goal: to send a probe to the Alpha Centauri system within a human generation, reaching it in roughly 20 years of flight. To do that, it would need to fly at about 1/5 of the speed of light, vastly faster than any craft before, and it proposed to reach that speed not with a rocket, but with light itself. The physics rests on a simple fact. Light carries momentum. When light strikes a surface, it gives that surface a tiny push. The push from ordinary light is far too gentle to feel, but concentrate enough light onto a light enough object, and the push becomes real propulsion. A light sail is a thin, mirror-like sheet that catches that push, the way a cloth sail catches wind, except the wind is a beam of pure light and the sail rides the pressure of the beam. Starshot's design is radical in its smallness. Instead of a giant ship, it imagines a tiny chip, a gram-scale spacecraft called a starship, carrying cameras, sensors and a power source, all shrunk to the size and weight of a small wafer. This chip is attached to a light sail just a few meters across, and only a few atoms thick, fantastically thin and light. The whole craft together would weigh no more than a few grams, lighter than a coin. By making the spacecraft almost nothing, the same push can fling it to extraordinary speed. The push would come from the ground. Starshot envisions an enormous array of powerful lasers on Earth, working together as one beam, aimed at the sail. For a few minutes, this combined laser would pour its energy onto the sail, accelerating the tiny craft to 1/5 of light speed before the probe coasts the rest of the way unpowered. The engine, in effect, stays home. Only the featherlight sail and its chip make the crossing, driven by light delivered from a distance. It is a clever escape from the rocket equation, because the ship no longer has to carry the fuel that pushes it. This approach turns the whole problem inside out. The crushing weight of propellant, the heart of every earlier failure, simply disappears, because the energy source never leaves the launch site. The spacecraft becomes almost massless, and a beam of light does the work that no onboard engine could. For the first time, a plan exists to reach Alpha Centauri not in tens of thousands of years, nor even in centuries, but within a couple of decades, a span a person could live to see from launch to arrival. Starshot is the closest thing we have to a real, physics-respecting path to the nearest star, and serious scientists treat it as worth studying and pursuing. But shrinking the ship to a few grams and flinging it at 1/5 of light speed does not make the difficulties vanish. It trades one set of impossibilities for another, and the price of going that fast in what the probe must give up and what it must survive is the next hard truth to face. A gram-sized chip racing at 1/5 of light speed sounds like a clean escape, but the speed itself extracts a heavy price, and that price reshapes the entire mission. To understand why reaching Alpha Centauri stays so hard even with a clever plan like Starshot, you have to look at everything that flying that fast forces you to surrender. The first sacrifice is size, and with it, capability. To be pushed to 1/5 of light speed by a beam of light, the probe must weigh only a few grams. That is a brutal limit. There is no room for a large camera, a big antenna, a nuclear power source, or any of the heavy, capable instruments that make our solar system probe so powerful. The Voyager craft and the Cassini mission to Saturn weighed hundreds or thousands of kilograms and carried rich suites of instruments. A starship must do everything with a sliver of that, a few grams of electronics riding a gossamer sail. The price of speed is that the explorer becomes almost nothing. The second sacrifice is the ability to stop. To slow down at the destination, a spacecraft needs to shed all the speed it gained, which means another vast push in the opposite direction, another engine or another beam waiting at the far end. Starshot has no way to do this. The probe cannot carry braking fuel, and there is no laser at Alpha Centauri to catch it. So it does not stop. It flies straight through the system at 1/5 of light speed, crossing the entire span around the target star in a matter of hours, grabbing what data it can during that brief, blazing pass. There is no orbit, no lingering study, only a single fleeting glimpse. The third sacrifice is the steadiness we take for granted in our local missions. At 1/5 of light speed, a probe covers tens of thousands of kilometers every second. Aiming such a craft precisely enough to pass close to a planet, 4 light-years away, after 20 years of unguided flight demands almost unimaginable accuracy at launch. A tiny error in direction at the start becomes an enormous miss across that distance. The faster you go and the farther you travel, the less room there is for the smallest mistake, and these sacrifices interact. A few grams of probe means a tiny antenna and a tiny power source, which means only the faintest whisper of a signal can be sent back across 4 light years. A flyby means only hours of observation after 20 years of travel. Extreme speed means extreme precision and no second chances. Each compromise that makes the journey possible also makes the mission thinner, briefer, and more fragile. The very tricks that let the probe go fast strip away nearly everything that would let it do much once it arrives. There is also a deeper exchange hidden in the choice. To make the trip survivable within a human lifetime, Starshot gives up the idea of a substantial spacecraft entirely. It accepts that the thing reaching Alpha Centauri will be a flake of technology, glimpsing the system once and falling silent, rather than a true explorer settling in to study a new world. It is a real plan, and it is a humble one, shaped at every turn by the punishing cost of speed. So even our best path to the nearest star is not a grand ship but a fragile mote, flung once across the dark, granted a few hours at its goal, whispering back the faintest of reports. Going fast enough to make the crossing in a lifetime means giving up nearly everything that would make the arrival rich. And as we're about to see, even this stripped-down feather of a craft must survive a journey through space that is far less empty and far more dangerous than it looks. Between the stars, space looks utterly empty, a perfect void with nothing in it for light years on end, and by everyday standards it nearly is. But nearly empty is not the same as empty, and at 1/5 of the speed of light, the thin scattering of matter drifting between the stars stops being harmless and becomes a serious threat. The very emptiness we count on hides a danger that grows worse the faster we go. Interstellar space is not a pure vacuum. It holds a faint haze of gas and tiny solid grains, what astronomers call interstellar dust. These grains are minute, often far smaller than a speck you could see, and they are spread incredibly thinly, perhaps one tiny grain in a great volume of space. A spacecraft moving slowly through this haze would barely notice it across an entire journey. At ordinary speeds, the dust between the stars is no obstacle at all, just a whisper of matter in an enormous dark. Speed changes everything, because the energy of a collision depends on how fast the two things meet. The faster you strike a particle, the harder the blow, and the relationship is steep. At 1/5 of light speed, a probe slams into each dust grain at 60,000 kilometers a second. At that velocity, even a microscopic grain carries a shocking amount of energy. A particle far too small to see, struck at such speed, hits like a tiny bullet, depositing a burst of energy that can vaporize material on contact. The emptiness has teeth, and the teeth are sharpened by speed. For Starshot's gossamer probe, this is a genuine hazard. The sail is only atoms thick, and the chip is tiny and fragile. Over 4 light years, the craft would plough through countless grains of dust, each impact at 1/5 of light speed punching, burning, or eroding a little of the structure. Larger grains, rarer but present, could destroy the probe outright in a single strike. The probe must survive 20 years of this steady bombardment, with no way to repair itself, arriving intact enough to still work. The thin and the fast are exactly the things least able to take such punishment. There are also the gas atoms, individual particles of hydrogen and other elements floating between the stars. Slamming into these at 1/5 of light speed is like being sprayed continuously with a faint beam of radiation, atom by atom striking the front of the craft, slowly damaging its materials over the years of flight. The faster the probe moves, the more violent each of these countless small encounters becomes, and the more they add up across the long crossing. Even the thinnest gas turns abrasive when met at such speed. This is one of the angles that the easy story of interstellar travel tends to skip. We picture the gap between stars as a clean, safe emptiness, and the only enemy is distance. But the same speed that conquers the distance turns that emptiness hostile. Going fast is the only way to cross in a lifetime, and going fast is precisely what makes the sparse matter along the way dangerous. The solution to one problem sharpens another, which is a pattern that runs through this whole subject. So the road to Alpha Centauri is not the smooth, empty corridor it appears to be. It is a thin haze of dust and gas that a slow traveller would never feel, transformed by tremendous speed into a gauntlet of tiny blazing impacts. Any probe fast enough to make the trip in decades must also be tough enough, or lucky enough, to run that gauntlet for 20 years and survive. The emptiness between the stars, it turns out, defends them, and the speed that would carry us across is the very thing that arms it. Suppose a probe does reach Alpha Centauri. It survives the dust, holds together, and sweeps past Proxima b with its cameras working. Now it has something to tell us, and here the distance returns in a new and quieter form. Whatever the probe sees, it must send home as a signal, and that signal can travel no faster than light. So even success comes with a long built-in silence. A radio message, or a pulse of laser light, crosses space at the speed of light and no faster. From Alpha Centauri, that means any signal the probe sends takes 4.37 years to reach Earth. The probe could fly through the system, gather its data, and beam everything back in a single triumphant burst, and we would still wait more than 4 years to receive the first bit of it. The news of arrival would already be over 4 years old by the time it landed in our antennas. This delay shapes the whole rhythm of such a mission. Imagine the probe launches and flies for 20 years to make the crossing. At the moment it streaks past the planet, the people on Earth know nothing yet. They must wait another 4 years and more for the light carrying the images to crawl home. So from the day the probe reaches its goal to the day we learn what it found, over 4 years pass in pure waiting, with the answer already on its way but not yet here. There is no trick to shorten this. The speed of light is the firm ceiling on how fast any information can travel, woven into the structure of the universe. We cannot ask the signal to hurry. Across 4 light years, every message is at least 4 years stale on arrival, and every question we might send back to the probe would take another 4+ years to reach it, if it could even still listen. A conversation across that gap would have single exchanges spanning the better part of a decade. The faintness of the signal makes the silence heavier still. A gram-sized probe can carry only a tiny transmitter and a tiny antenna, so the message it sends across 4 light years arrives almost unimaginably weak. A whisper spread thin across an ocean of distance. Catching it would demand enormous sensitive receivers on Earth, straining to hear a signal close to vanishing into noise. The probe shouts with all its meagre strength, and what reaches us is the faintest trace, gathered over the long delay. So the reward for crossing to the nearest star is not immediate. It is a long wait for a faint delayed report, years after the probe itself has done its work and likely fallen dark. The mission's success and our knowledge of it are separated by the same gulf that made the journey so hard. The simple, unyielding width of 4 light years. Distance taxes us coming and going, in the travel out and in the news back. This is worth holding on to because it reframes what reaching Alpha Centauri would even feel like. There would be no live broadcast, no moment of shared discovery as it happened. There would be a launch, then decades of patience, then a flyby no one on Earth could yet see, then more years of silence, and finally a thin signal arriving from a probe that was already long past its goal and probably gone. Even triumph across this gap comes muffled and late, carried home at the slow pace of light through a very long night. Step back from any single design and ask a blunter question. How much raw energy would it actually take to send something meaningful across to Alpha Centauri at a useful speed? Not the cleverness of the engine, but the sheer quantity of power involved. When you work it out, the answer reveals why this is less an engineering puzzle than a question of civilizational scale. Energy is what speed costs. To accelerate a mass to a given velocity takes a definite amount of energy, fixed by physics, no matter how you deliver it. The faster you want to go, the more energy you need, and the relationship climbs steeply as speeds grow large. To push even a small payload to 1/5 of the speed of light requires an amount of energy that dwarfs the output of our largest power plants, not for a moment, but poured out in a concentrated burst. Consider Breakthrough Starshot's own numbers. To accelerate its tiny gram-scale sail to 1/5 of light speed, the ground-based laser array would need to deliver in just a few minutes a burst of power comparable to a substantial share of all the electrical generating capacity on Earth. For those few minutes, the laser would draw on energy at a rate that rivals the output of entire nations, focused into a single beam aimed at a sliver of material. And that is for a probe lighter than a coin, carrying no people and no way to stop. Now imagine scaling up. Suppose you wanted to send not a gram, but a real spacecraft, with instruments, a power source, and the ability to slow down and stay. The energy required does not rise gently. It multiplies enormously with the added mass and with the braking. With a crude ship, vastly heavier, slowing at the far end, would demand energy on a scale that strains comprehension, comparable to the total energy a civilization might use over long stretches of its history, concentrated into a single voyage. This is why some thinkers measure starflight not in fuel, but in the energy budget of a whole civilization. To cross to even the nearest star with a substantial ship is to spend power on a scale that our current species, harnessing the energy we do, simply does not command. We light our cities, run our industries, and fly our jets on a global energy supply that is a small fraction of what one serious interstellar crossing would consume. The trip is not expensive in the way a bridge or a rocket is expensive. It is expensive in the way that reshaping our entire relationship to energy is expensive. That reframing is the quiet point of this chapter. The barrier to Alpha Centauri is not only that we lack the right engine, it is that the energy demanded by the journey sits far above what we presently produce or could readily produce. To send a meaningful mission, a civilization would likely need to draw on power sources far beyond today's, harnessing sunlight or fusion on a scale we have only imagined. The gap to the nearest star is in part a gap between the energy we use now and the energy such a crossing requires. So the difficulty is structural, woven into the physics of speed and the limits of our power. Even granting clever engines and fragile probes, the raw energy bill remains staggering, and it grows monstrous the moment you ask for anything more than a feather flung once across the dark. The nearest star is held away from us not only by distance and time, but by a wall of energy that marks the difference between the civilization we are and the one we would have to become. There is a strange twist in all of this, a reason that even a civilization able to launch might choose to wait. It comes from a simple observation about progress. If our spacecraft keep getting faster over time, then a probe launched later, with a better engine, could overtake one launched earlier. Sometimes the wisest move is not to go now, but to wait for a faster ship. This idea has a name. It is called the weight calculation, studied carefully by the researcher Andrew Kennedy. The reasoning runs like this. Imagine you launch a probe to Alpha Centauri today, at the best speed you can manage, and it will take, say, 1,000 years to arrive. Now imagine that over the coming centuries propulsion keeps improving, as it has improved in the past. A probe launch 200 years from now might be fast enough to pass your first probe along the way and reach the star sooner, despite leaving much later. If that is true, then launching immediately is a mistake. Your early slow probe spends centuries crawling through space, only to be overtaken by a craft that left long after it. You would have arrived sooner by staying home, letting technology mature and launching a faster vessel later. There is in this view an optimal moment to depart, a sweet spot where waiting any longer no longer helps because the gains in speed have leveled off. Leave before that moment and a future ship beats you. Leave after and you have simply delayed for nothing. Kennedy tied this to a notion he called the incessant obsolescence postulate. The word obsolescence captures it well. As long as our ships keep getting better at a steady pace, any ship we launch is destined to be made obsolete by a better one behind it, the way a computer bought today is outpaced by next year's model. Under that postulate, early starships are doomed to be passed, and the rational traveller waits for the improvement to slow before committing to the long crossing. The idea cuts in a sobering direction for those eager to go now. It suggests that the very best thing an impatient civilization could do, if it truly wanted to reach Alpha Centauri first, might be to not launch yet, but to invest in faster engines and hold off. The journey is so long that decades or centuries of waiting on the ground can be repaid many times over by a higher speed at departure. Patience, counterintuitively, can be the fastest route across. But the weight calculation also has a darker reading. It quietly assumes that progress continues, that our descendants keep improving propulsion century after century until the curve flattens. If progress stalls, or a civilization turns inward, or the steady advance simply stops, then the perfect ship that justified the waiting never arrives. The wait becomes endless, the launch forever deferred to a tomorrow that does not improve. The reason to wait can become, if we're not careful, a reason to never go at all. So the weight calculation adds a subtle layer to the difficulty of Alpha Centauri. Even setting aside fuel and energy, there is a real argument that the right time to launch is not now, and possibly not soon, and that any probe sent today would likely be overtaken by a better one yet to be built. The nearest star recedes not only behind walls of distance and power, but behind the strange logic of progress itself, which whispers, again and again, that it might be wiser to wait a little longer. For most of this story, we have spoken of probes, small machines flung across the dark. But the oldest dream is to send people, and that brings a different kind of difficulty, one measured not in fuel, but in human lives and the span of generations. If no engine can carry a crew there within a single lifetime, then perhaps the answer is a ship built to outlast the people who first board it. This is the idea of the generation ship. The concept is stark and strangely moving. You build an enormous vessel, a small sealed world, and you send it toward another star at whatever speed you can manage, knowing the journey will take centuries or more. The people who step aboard at launch will never see the destination. They will live their whole lives in transit, raise children, grow old, and die in the ship. Their descendants, born in the dark between stars, will carry the mission forward until some distant generation, many removed from the first, finally arrives. The human weight of that is hard to hold. Everyone who boards is choosing not just their own life in a metal world, but the lives of children and grandchildren who never consented, born into a journey they cannot leave. Generations would live and die having known nothing but the inside of the ship, the same corridors, the same recycled air, the same enclosed sky. They would inherit a mission decided long before their birth, bound to a purpose chosen by ancestors they never met, carrying it toward a star they may never reach. There are deep practical problems layered onto the human ones. A generation ship must keep a closed world alive for centuries without resupply, growing all its food, recycling all its water and air, and repairing everything that breaks, with no outside help across the whole crossing. It must hold a stable society together for many generations in a confined space, avoiding the collapse, conflict, or simple forgetting that could doom the mission. A community sealed in a vessel for hundreds of years could lose its purpose, its knowledge, or its will long before arrival. And it is almost certainly a one-way trip. The people who leave are gone for good, and so are all their descendants until the end. There is no return, no rescue, no second chance if something goes wrong far from home. The first crew says goodbye to Earth, knowing that neither they nor their children, nor likely their children's children, will ever come back, and that everyone they wave to will be long dead before the ship arrives. It is a farewell across not just space but time. This is why generation ships remain for now more a subject of thought and fiction than of engineering plans. They ask not only whether we can build a sealed world that survives for centuries, which we cannot yet do, but whether it is right to commit unborn generations to a closed voyage they never chose. The difficulty is moral as much as technical, and it does not soften with better machines. Even a perfect ship still carries the question of the lives lived and ended inside it. So the dream of sending people to Alpha Centauri runs into a wall that no engine can breach. Either we find a way to travel fast enough for a crew to arrive within their own lives, which lies far beyond us, or we accept the slow, heavy, generations-long crossing with all its human cost and all its risk of failure across the centuries. The nearest star, for living people rather than machines, asks not only for power and patience, but for the willingness to send our descendants into the dark on a journey none of them will choose. Set aside the long generations for a moment and look at what space does to a single human body over even a shorter crossing. Long before a ship reaches Alpha Centauri, the people inside it face an enemy that needs no centuries to do harm. Deep space is bathed in radiation, and a living body, away from the shelter of Earth, is exposed to it in a way that slowly, steadily breaks it down. On Earth, we are protected by two great shields. The planet's magnetic field deflects much of the charged particle radiation streaming from the sun and beyond, and the thick atmosphere absorbs much of the rest. We live our whole lives at the bottom of this double shelter, rarely aware of the storm of high-energy particles it holds back. Step beyond it, into deep space, and both shields fall away. A spacecraft far from Earth is exposed to the full radiation environment of the cosmos. Two sources matter most. The sun throws out bursts of charged particles, especially during solar storms, that can flood a region of space with dangerous radiation in a short time. And from far beyond the solar system come cosmic rays, atomic nuclei accelerated to tremendous energies by distant violent events, raining in from all directions at all times. These cosmic rays are especially hard to stop, so energetic that they punch through ordinary shielding and through human tissue alike, leaving damage in their wake. What this radiation does to the body is the heart of the danger. As these high-energy particles pass through living tissue, they break apart the delicate molecules inside cells, including the DNA that carries the instructions for life. The body can repair some of this damage, but a steady years-long exposure overwhelms that repair. Over time, the accumulated harm raises the risk of cancer, damages the heart and blood vessels, and can injure the brain and nervous system. A long voyage through deep space slowly wounds the traveller at the level of individual cells. The trouble is that shielding against it is heavy and imperfect. To block cosmic rays well, you need thick layers of material around the crew, and thickness means mass, and mass is exactly what every starship struggles to afford. Worse, when cosmic rays strike shielding, they can shatter into showers of secondary particles that are themselves harmful, so a poorly chosen shield can make things worse rather than better. Protecting a crew across years of deep space, while keeping the ship light enough to move, is a problem we have not solved even for the much shorter trip to Mars. This is why radiation sits among the quiet, stubborn obstacles to any crewed journey to Alpha Centauri. We tend to picture the dangers of starflight as dramatic, the failed engine, the collision. But one of the surest threats is invisible and constant, a slow rain of particles that the human body was never built to endure outside Earth's shelter. The longer the voyage, the heavier the dose, and a crossing to the nearest star, even at high speed, would expose a crew to far more than any human has yet survived. So before we even reach the strangeness of the destination, the journey itself threatens the travellers in a fundamental way. The same deep space that looks so calm and empty is steeped in radiation that erodes the body cell by cell across the years. To send people to the nearest star is to keep them alive and whole through a bath of cosmic particles for a span far longer than anyone has faced, and that, like so much else in this story, lies beyond what we can presently do. Even if we shielded the body from radiation, we would still have to keep it fed, watered, and breathing for the whole crossing, with no help from Earth. That means building a sealed world that recycles everything and sustains life on its own for years or generations. We have tried, in a small way, to build such a world here on the ground, and the attempt showed just how hard a closed life support system really is. The experiment was called Biosphere 2, built in the Arizona desert in the late 1980s and early 1990s. It was an enormous sealed glass and steel structure, enclosing several artificial ecosystems, a patch of rainforest, a small ocean, a savanna, a desert, and farmland to grow food. The idea was bold and direct. Seal a group of people inside, along with plants, animals, and soil, and see whether this miniature world could sustain them entirely on its own, recycling air, water, and food in a closed loop, the way Earth does on a vast scale. In 1991, 8 people sealed themselves inside Biosphere 2, intending to live there for 2 years, cut off from outside supplies of air, water, and food. The project was meant to test, in part, the kind of self-contained life support a long space voyage or an off-world colony would need. If a sealed world could work here, on Earth, with all our advantages, it might one day work aboard a ship or on another planet. The crew grew their own crops, tended their ecosystems, and tried to keep their small world in balance. It proved far harder than expected. The oxygen inside slowly and mysteriously declined, falling low enough that fresh oxygen eventually had to be pumped in from outside to keep the crew safe, breaking the seal the project was built to maintain. Growing enough food was a constant struggle, and the crew often went hungry. Many of the animal and insect species died off, while some pests thrived and spread. The balance of the tiny world kept tipping, and the people inside spent much of their energy simply fighting to keep it from collapsing. The lesson was humbling. Even with Earth's gravity, Earth's sunlight, and a team able to call for help, building a small sealed world that stays in balance turned out to be enormously difficult. The natural cycles that keep our planet livable, the ones that quietly recycle our air and water and feed us, are the product of a whole world's worth of interconnected systems, and shrinking them into a building proved beyond easy reach. Biosphere 2 did not fail completely, but it revealed how delicate and demanding a closed life support system is. Now carry that lesson into space. A ship bound for Alpha Centauri would need a sealed world that works not for 2 years on a calm Earth, but for decades or centuries in deep space, far from any rescue, with no fresh oxygen to pump in when the balance fails. It would have to recycle every breath and every drop of water, grow all its food, and keep its ecosystem stable across a span longer than any human institution has reliably lasted. Biosphere 2 suggests how far we are from that, having stumbled over a much gentler version of the same task. So the quiet, unglamorous problem of life support stands alongside the dramatic ones of speed and energy. To send people to the nearest star, we must learn to carry a living piece of Earth with us, sealed and self-sustaining, for the whole long dark. Our one serious rehearsal for that, a glass world in the desert, struggled to last 2 years. The gap between that and a ship that sustains life across the Gulf to Alpha Centauri is one more wide space we have not yet learned to cross. Suppose, against all these odds, that a probe or a ship does arrive. It is worth asking what waits at the other end, because the destination itself is far less welcoming than the bright dream suggests. The most likely target, the Earth-sized world Proxima b, orbits a star that does something dangerous to it, and understanding that danger changes how we think about going at all. Proxima Centauri, the faint red dwarf that hosts the planet, is not a calm, steady star like our Sun. It is a flare star prone to sudden, violent outbursts. Red dwarfs of its kind store magnetic energy and release it in abrupt, powerful flares, far larger relative to the star's size than the flares our Sun produces. In moments, Proxima can brighten dramatically, hurling out a burst of radiation and charged particles. These are not rare, gentle flickers. They are frequent, intense eruptions from a star that seems quiet only because it is so dim. The problem for Proxima b is its closeness. Because the star is faint and cool, the planet must orbit very near to it to be warm enough for liquid water, completing a full circuit in only about 11 days. That tight orbit puts the planet directly in the path of the star's fury. When Proxima flares, the radiation and particles strike Proxima b far harder than a similar flare would strike a planet at Earth's comfortable distance from the Sun. The very nearness that makes the world warm also makes it terribly exposed. What such flares can do to a planet is severe. Repeated powerful bursts of radiation can strip away a planet's atmosphere over time, tearing molecules from the upper air and letting them escape into space. The same flares can flood the surface with harmful radiation, the kind that would damage living cells. A world battered for billions of years by frequent intense flares might be left with little or no atmosphere, its surface scoured, its chances for liquid water and life sharply reduced. The flares are a slow, repeated assault on whatever the planet once held. So the most tempting target, the Earth-sized world in the habitable zone of the nearest star, may not be the gentle haven its placement suggests. It sits close to a small, restless star that erupts again and again, and that closeness, required for warmth, exposes it to a punishing radiation environment we do not face on Earth. The habitable zone, defined only by temperature, does not account for a star that periodically burns its planet. Proxima b may be warm enough for water and still be a harsh, irradiated place. This matters deeply for the dream of going there. Part of what makes Alpha Centauri so alluring is the image of a second Earth waiting at the end of the journey, a world to study, perhaps even to live on. But if the nearest planet around the nearest star is a flare-scoured world with a stripped atmosphere, the prize at the end of the impossible journey may be far less than we hope. The difficulty of reaching it is matched by the uncertainty of what reaching it would gain. None of this is certain. We do not yet know whether Proxima b has held onto an atmosphere, or whether some shelter allows water to persist despite the flares. That uncertainty is honest and real, but it sharpens the whole picture. The nearest star is not only hard to reach, the world it offers may itself be hostile, burned repeatedly by the small fierce star it circles, a reminder that nearness and welcome are not the same thing, and that the door at the end may open onto a harsher room than we imagined. There is one more strange feature of the worlds we would aim for, and it follows from the same closeness that exposes them to flares. A planet orbiting so near to its small star is likely caught in a gravitational grip that stops it from turning freely, fixing one face forever toward the star and leaving the other in endless night. This is tidal locking, and it gives these worlds a climate unlike anything on Earth. Tidal locking comes from the pull of gravity acting unevenly across a planet. A star tugs slightly harder on the near side of a planet than the far side, and over long ages this difference acts like a brake on the planet's spin. For a world orbiting close to its star, the braking is strong, and eventually the planet's rotation slows until it turns exactly once for each orbit. From then on, the same hemisphere always faces the star, just as the same face of the moon always faces the Earth, for the very same reason. The moon is tidally locked to us, which is why we never see its far side from the ground. For a planet like Proxima b, this likely means a permanent day side and a permanent night side. One half of the world lies under a star that never sets, bathed in constant red light and warmth. The other half is turned forever away, trapped in unending darkness and deep cold. There is no sunrise, no sunset, no day and night as we know them. The sky is frozen in place, the star fixed at the same spot above the day side, hanging motionless wherever you stand. The climate of such a world would be extreme and lopsided. The day side under steady starlight could grow very hot, especially the point directly beneath the star. The night side, never warmed, could grow brutally cold, cold enough to freeze the air itself in the worst cases. Between them would run a band of perpetual twilight, a ring where the star sits low on the horizon, possibly the most temperate region of all. Whatever liquid water or life such a world might hold could be confined to that narrow twilight zone, caught between fire and ice. Whether such a planet can remain livable depends on details we do not fully understand. A thick enough atmosphere or a deep enough ocean might carry heat from the scorched day side to the frozen night side, spreading warmth and softening the extremes, much as winds and currents move heat around the Earth. Without such circulation, the contrast could be lethal, the day side baked and the night side frozen solid. The habitability of a tidally locked world hangs on questions of air and water flow that we're only beginning to explore. If you find this slow walk through the nearest star worthwhile, consider subscribing so the next quiet journey finds you too. So the worlds around the nearest stars are stranger than the simple phrase Earth-sized planet suggests. They may be locked in place, half scorched and half frozen, their living room reduced to a thin ring of twilight, if they are livable at all. The familiar rhythm of day and night, which shapes every living thing on Earth, would be absent entirely. To picture standing on Proxima b is to picture a fixed red star burning in one spot of an unchanging sky, casting long shadows that never move. This is one more way the nearest star resists the easy dream. Not only is it desperately hard to reach and orbited by a flare-prone host, but its most promising world may be a locked, lopsided place unlike any home we know. The destination, like the journey, refuses to be simple. Nearness once again turns out to be the beginning of the difficulty rather than the end of it. Through all of this, it is easy to imagine Alpha Centauri as a fixed point, sitting patiently at 4 light-years while we figure out how to reach it. But the stars are not still. They move through the galaxy, each on its own path, and Alpha Centauri is moving too, drifting slowly in relation to the Sun. Over the long ages, that motion changes the distance between us, and it is changing it now in an interesting direction. Every star in the sky is in motion, orbiting the centre of the galaxy and drifting relative to its neighbours. We do not see this with our eyes because the stars are so far away that their movement across our sky is achingly slow, taking many thousands of years to shift noticeably. But the motion is real and measurable. Astronomers track how stars move both across our line of sight and toward or away from us, building a picture of the slow currents of the galaxy. Against this background, Alpha Centauri is not parked. It is travelling. Right now, Alpha Centauri is approaching the Sun. It is moving toward us, slowly closing the gap between our two systems. Over the coming tens of thousands of years, it will continue to draw nearer, shrinking the distance from its current 4.37 light-years. The nearest star is, very gradually, becoming nearer still, creeping closer at a pace far too slow to feel, but steady across the long span of time. This approach will not go on forever. Alpha Centauri will reach a closest point, drawing in to a little under its present distance, perhaps around 3 light-years, in roughly 25 to 30,000 years from now. At that moment it will be the nearest it ever comes, the gap between our systems at its narrowest. After that, the motion carries it onward and away, and the distance will begin to widen again. The stars pass each other like ships in a vast slow sea, nearing and then parting. The change is real but modest. Even at its closest approach, Alpha Centauri will still be around 3 light-years away, only a little nearer than it is today. The improvement is not enough to rescue any of the journeys we have considered. A trip that takes tens of thousands of years at 4 light-years still takes tens of thousands of years at 3. The star's slow approach trims the distance by a fraction, not by the enormous factor that would turn the crossing from impossible into easy. Still, it adds a quiet dimension to the whole question. The nearest star is not a permanent fixture but a passing neighbour, drifting closer over the next tens of thousands of years and then receding again across the ones after that. If there is ever a time when Alpha Centauri is most reachable by distance alone, it lies far in the future, longer from now than all of human history reaches into the past. The window, if it is a window, opens on a timescale that dwarfs our entire civilization, so even the distance itself is in slow motion, easing nearer and then pulling away over spans of tens of thousands of years. It is a reminder that on the scale this subject demands, nothing is truly fixed, not even the gap to the nearest star. The galaxy turns, the stars drift, and Alpha Centauri leans toward us for a while before leaning away, indifferent to whether we ever find a way to cross the space between. The star's slow approach raises a tempting thought. If Alpha Centauri is drawing nearer, and if our technology is improving, then maybe there is a single best moment to launch, a perfect window where distance and capability line up. It is worth asking seriously whether such a moment ever truly arrives, because the answer reveals something about how this whole problem is shaped. Two slow changes are in play at once. The first is the star's motion, bringing Alpha Centauri gradually closer over the next tens of thousands of years before it recedes again. The second is the possible improvement of our spacecraft, the steady gain in speed imagined by the weight calculation, where each generation builds faster engines than the last. In principle, the ideal time to leave would be when the combination is most favourable, when the star is near enough and our ships are fast enough that the crossing is at its shortest. But the two changes run on wildly different clocks. The star's approach unfolds over tens of thousands of years, far too slowly to matter on any human timescale, and it only trims the distance by a small fraction even at its best. Technological progress, if it continues, moves much faster, potentially transforming our speed over mere centuries. So the star's motion is almost irrelevant to the timing. The real question of when to launch hangs almost entirely on how fast our ships become, not on how near the star drifts. And here the weight calculation bites again. As long as our engines keep improving, any ship we launch risks being overtaken by a faster one behind it, which argues for waiting. But waiting only pays off if the improvement actually continues and then levels off, giving a clear best moment to go. If progress never quite stops, the perfect ship is always just ahead, and the launch is forever deferred. The window does not so much open as keep sliding into the future, always a little further on. There is a deeper trouble. A true launch window assumes we will one day have the capability to make the crossing at all, that the energy, the engines, and the life support will exist, and only the timing remains in question. But as we have seen, that capability lies far beyond us, behind walls of energy and engineering we do not yet know how to climb. You cannot choose the best time to leave until you can leave, and we cannot yet leave. The window cannot open while the door itself is still sealed. So the honest answer is that no clear launch window is in sight. The star's helpful approach is too slow and too slight to set the timing. The promise of faster ships, if it holds, pushes the best moment ever forward, rather than fixing it. And beneath both lies the simple fact that we lack the means to make the journey at all, which makes the question of timing premature. Asking when to leave assumes a readiness we have not reached. This does not mean the moment will never come. It means that, as things stand, there is no point on the calendar where the path to Alpha Centauri clearly opens. The factors that might create a window, the star's drift and our growing skill, either move too slowly to matter or keep the ideal moment receding. For now, the best time to leave is not a date we can name, but a horizon that stays ahead of us, a reminder that we're not yet choosing when to go, but still struggling with whether we can go at all. It is worth pausing here to clear up a confusion that often tangles discussions of cosmic distance. When people hear that some things in the universe are unreachable, they often think of the expanding universe, the way distant galaxies are racing away from us and slipping permanently out of reach. That is a real effect, but it is a completely different problem from the one we face with Alpha Centauri, and keeping them separate sharpens what the nearest star's difficulty really is. The expanding universe describes how space itself is stretching on the larger scales. Far-off galaxies are moving away from us, and the most distant ones recede so fast, carried by the expansion of space, that their light will never reach us and we could never reach them no matter how fast we travelled. For those remote galaxies, the distance grows faster than any ship could close it. They are unreachable in a deep, permanent way, walled off by the expansion of the cosmos itself. Alpha Centauri has nothing to do with this. The expansion of the universe acts only across enormous cosmic distances, between galaxies separated by millions and billions of light years. Within our own galaxy, and certainly within the tiny span of 4 light years to the nearest star, the expansion is utterly irrelevant. Gravity holds our galaxy together against the stretching of space, so the stars around us are not being carried away by cosmic expansion at all. Alpha Centauri is not receding because the universe is growing. It is a near neighbour, bound with us in the same galaxy. This is a crucial distinction. The difficulty of reaching distant galaxies is woven into the fabric of the cosmos, a fundamental limit set by the expansion of space, against which speed is no help because the distance itself outruns light. The difficulty of reaching Alpha Centauri is nothing like that. The star is not fleeing us through expanding space. It sits at a fixed, modest distance, even drifting slightly closer for now. The gap is not growing beyond our reach. It is simply, stubbornly, very wide. So the two impossibilities are of entirely different kinds. Distant galaxies are unreachable because the universe forbids it, because they recede faster than light can travel and no conceivable ship could catch them. Alpha Centauri is hard to reach for reasons that are in a sense ordinary. The distance is large, our speeds are small, the energy required is immense, and the human and engineering problems are severe. None of these are cosmic laws sealing the door. They are practical barriers, towering but not woven into the structure of space itself. That difference matters for how we think about the word impossible. The unreachable galaxies are impossible in the strongest sense, ruled out by physics no matter what we do. Alpha Centauri is not impossible in that way. Nothing in the laws of nature forbids a ship from crossing 4 light years. The obstacles are about means, not permission, about what we can build and power and endure, not about what the universe allows. Holding this distinction clearly is the key to the next step. The trouble with the nearest star is not that the cosmos has placed it beyond reach, the way it has placed the far galaxies beyond reach. The trouble is of a more human and more practical kind, vast in scale but different in nature. And that raises the central question this whole journey has been circling toward. When we say Alpha Centauri may already be impossible to reach, what kind of impossible do we actually mean? So we come to the heart of the matter, the word that has hung over this entire journey. Is Alpha Centauri impossible to reach? The answer depends on which kind of impossible we mean, and sorting the two kinds apart is the most important thing this whole exploration can do. There is impossibility written into the laws of nature, and there is impossibility that comes from the limits of what we can practically do, and they are not the same. Physical impossibility is the hard kind. Some things are forbidden by the laws of physics themselves, and no amount of effort or cleverness can ever achieve them. Travelling faster than light is one such thing, ruled out by the deepest principles we know. Reaching the most distant galaxies, carried away by cosmic expansion faster than light, is another. These are not merely difficult, they are barred, closed by the structure of reality, and they will remain closed no matter how advanced we become. Against physical impossibility, there is no engineering answer. Reaching Alpha Centauri is not impossible in that sense. Nothing in the laws of physics forbids a ship from crossing 4 light years. Light makes the trip in a little over 4 years. A ship travelling at a large fraction of light speed could, in principle, make it within a human lifetime, and the physics of such a journey, while extreme, breaks no laws. The destination is fixed, near, and reachable in principle. On the question of physical possibility, the door to Alpha Centauri stands open. What blocks us is the other kind, practical impossibility. This is the impossibility of things that physics permits, but that lie utterly beyond our means, perhaps forever. The energy required is staggering, far beyond what our civilization produces. The engines needed do not exist and may never be built. The fuel demanded is impossible to gather or store. The human body cannot yet survive the journey, and we cannot yet build a sealed world to keep it alive. None of these are forbidden by nature, and all of them are, for now and the foreseeable future, beyond us. Permitted, yet unreachable in practice. The distinction is not a comforting loophole. Practical impossibility can be just as final as the physical kind, if the means never come within reach. A thing that the laws allow but that requires more energy than a civilization can muster, engines it cannot build, and lifespans it cannot extend, is impossible in every way that matters to the people who want to do it. The universe saying it is permitted offers cold comfort if we can never assemble what it takes. The door is open, but the threshold may stand forever beyond our step. And yet the difference does carry a thread of meaning. Because reaching Alpha Centauri is only practically impossible, not physically forbidden, it remains open to the slow work of progress in a way the distant galaxies never will be. A more advanced civilization, harnessing far greater energy, might one day do what we cannot. The barrier is high, perhaps higher than we will ever climb, but it is not a wall built into the cosmos. It is a wall built from our own limitations, and limitations, unlike laws of nature, can in principle change. So when we say Alpha Centauri may already be impossible to reach, we mean it in this precise and sobering way. Not that the universe forbids the journey, but that the journey lies so far beyond our power that, for us as we are, it might as well be forbidden. The nearest star sits at the strange border between the permitted and the achievable, close enough to see, allowed by every law, and still, in any practical sense, out of reach. Having faced the full weight of that difficulty, it helps to come back down to what we could actually do, the modest, real mission that sits at the very edge of our reach. Not a crude ship, not a substantial probe that stops and stays, but the smallest, humblest thing that might cross the gap within a human lifetime. When you strip away the dreams, this is what remains, and it is worth seeing clearly. The plausible mission is something like Breakthrough Starshot, a tiny gram-scale probe pushed by a ground-based laser to about a fifth of light speed. This is the one approach that does not demand undiscovered physics or impossible quantities of fuel. It leaves the heavy engine on Earth, makes the spacecraft almost nothing, and uses light to do the pushing. Of all the ideas we have explored, it is the only one that even sketches a path to Alpha Centauri within a span a person might live to see, from launch to arrival in roughly 20 years. But notice how modest this real mission is. It carries no people. It does not slow down or stop. It flies straight through the Alpha Centauri system at a fifth of light speed, taking what data it can in a few short hours, then continues on into the dark beyond, never to return. It is a flyby of the briefest kind, a single fast pass with no second look. The grand vision of going to another star shrinks, in the realm of the actually possible, to a feather-light chip glimpsing the system once as it streaks through. Even this stripped-down mission is not yet within our grasp. It would require building a laser array of staggering power, far beyond anything that exists, capable of delivering enormous energy in a focused beam. It would require making sails only atoms thick that can survive that beam without tearing or melting. It would require shrinking a working spacecraft with camera, sensors and transmitter down to a few grams and having it survive 20 years of dust and radiation, then send a detectable signal home across 4 light years. Each of these is a formidable challenge, and none is yet solved. So even the humblest real path to the nearest star sits at the outer limit of our ability, demanding advances we have not made. It is not impossible in the way a crude generation ship is impossible. It is closer, more concrete, the subject of actual study by actual scientists. But it remains a stretch beyond today's technology, a goal that would take decades of development even to attempt, and then decades more of flight, and then years of waiting for the faint signal to crawl back. This is what reaching Alpha Centauri realistically looks like, at least for now. Not a starship with a crew waving from the bridge, but a tiny chip on a thin sail, flung once across the dark by a laser we have not yet built, glimpsing the nearest star in passing and falling silent. It is a long way from the dream, and it is the closest the dream comes to the possible, and yet, modest as it is, such a mission would not be nothing. A single fast pass through the Alpha Centauri system, even in a few brief hours, could still teach us things we cannot learn any other way, and it is worth pausing to see just how much a humble flyby might reveal. It would be easy to dismiss a flyby as too brief to matter, a few hours of data after 20 years of flight. But that would be a mistake. Even a single fast pass through the Alpha Centauri system, by even a tiny probe, could reveal things that no telescope at Earth, however large, will ever show us. The value of being there, even for a moment, is greater than it first appears. The reason is distance, the same distance that makes the journey so hard. From Earth, even our finest telescopes see the planets of other stars only as faint tugs on their star, or as shadows crossing its face, or at best as single dim points of light. We cannot see their surfaces, their continents, their weather, their detail. The planets around Alpha Centauri are from here essentially invisible as worlds, known only through indirect signs. There is a limit to what we can learn from 4 light-years away, no matter how clever our instruments at home. A probe that actually flies through the system shatters that limit. Even passing at a fifth of light speed, even in a few short hours, a probe near Proxima b could capture something we can never get from Earth. A close look at the planet itself. It could photograph the world, however briefly, revealing whether it has an atmosphere, clouds, oceans, or land. It could measure the planet directly, sensing its conditions up close rather than guessing from afar. A single pass at close range carries more raw truth about that world than centuries of watching from home. There is more such a probe could do along the way and on arrival. It could study the space between the stars firsthand, sampling the dust and gas that no spacecraft has ever crossed, mapping the medium that fills the gap. It could examine the stars of Alpha Centauri up close, measuring their light and behaviour in detail impossible from Earth. It could search for more planets, smaller or fainter than those we've found, hidden in the system's depths. Every hour near the target would deliver a flood of first-hand knowledge about a place we have only ever seen as points of light. The contrast with our present knowledge is stark. Today, everything we know about Alpha Centauri's planets comes from indirect clues gathered across 4 light-years, clever but limited. A flyby would replace those clues with direct observation, the difference between inferring a thing and seeing it. The question of whether Proxima b holds an atmosphere, whether it has water, whether it could host life, might be answered in a single afternoon of close passage after being unanswerable from Earth for as long as we care to wait. So even the humblest mission we could realistically send would not be a token gesture. It would be a genuine act of discovery, transforming the nearest star from a set of distant inferences into a place we have actually visited, however briefly. The brevity of the pass is real, but so is the richness of being there, and a few hours at Alpha Centauri could rewrite our understanding of what lies at the doorstep of the galaxy. This is the quiet hope tucked inside all the difficulty. The journey may be at the very edge of the possible, the destination harsh, the mission tiny and fleeting, and still, if we could manage even that small thing, we would learn more about the nearest star in a single passing glance than in all the years of watching it from afar. The difficulty is enormous, and so, even at its smallest, is the reward. After this long walk through distance, time, energy, and the limits of what we can build, something unexpected comes into view. The difficulty of reaching Alpha Centauri turns out to be a kind of mirror. Held up to the nearest star, it reflects back not just facts about space, but a portrait of ourselves, of what we are and what we are not, of the size of our reach against the size of our dreams. The first thing the mirror shows is how young and small our powers still are. We have walked on the moon, sent machines to every planet, and touched the edge of the sun, and these are real achievements, the work of a species barely a few centuries into the age of science. And yet, set against the gap to the very nearest star, all of it falls short by a vast margin. The mirror reveals a civilization that has done astonishing things within its own solar system, and stands almost helpless before the smallest step beyond it. The second thing it shows is the strange shape of our knowledge. We understand the problem with remarkable clarity. We can calculate the distance, the energy, the time, the radiation, the dust, with confidence and precision. We know in fine detail exactly why we cannot go. There is something humbling in that, to comprehend a barrier so thoroughly and still be unable to cross it. The mirror shows a species that has learned enough to measure the wall precisely, and not yet enough to climb it. The mirror also reflects something about ambition and patience. The dream of reaching another star is, in a sense, a dream that outruns any single human life, any single generation, perhaps any version of civilization we would recognize. To take it seriously is to think in spans of centuries and millennia, to imagine descendants and successors far beyond ourselves. The difficulty of Alpha Centauri asks whether we can hold a purpose across such depths of time, and that is as much a question about human nature as about physics, and the mirror shows finally what it might mean to keep wanting this anyway. Knowing all the obstacles, understanding that the nearest star may lie beyond us for as long as we can foresee, people still study the problem, still sketch the probes, still point their arrows at Alpha Centauri. There is something in that persistence worth seeing. The difficulty does not extinguish the reaching. It clarifies it, strips it of easy illusion, and leaves a harder, clearer wanting underneath. So the nearest star teaches us about Earth as much as about space. It measures the distance between the civilization we are and the one we would need to become, a civilization commanding far greater energy, far longer patience, far deeper capability. It marks how far we have come and how immensely far we have to go. The gap to Alpha Centauri is, in the end, a way of seeing the gap between our reach and our reach's horizon, between what we can do and what we long to do. This is why the difficulty is worth dwelling on, not as discouragement but as understanding. To look hard at why we cannot reach the nearest star is to look hard at ourselves, at the true scale of our abilities and the true size of our hopes. The wall that holds us back is also a measuring rod, and what it measures is us. The nearest star, simply by being out of reach, tells us something honest about who is doing the reaching. We began on a clear night in the southern sky, with two bright points that turned out to be one nearest sun. We have walked the whole length of the gap since then, through distance and time, through engines that fail and engines that barely might work, through the harshness of the destination and the limits of ourselves. Now we return to where we started, to that quiet light low in the south, and let the wonder settle into something simpler. Alpha Centauri is still there, exactly as it was, 4.37 light-years away, a double sun with a faint red companion, the nearest star to our own. Nothing we have learned has moved it an inch. It hangs in the southern sky tonight as it has for all of human history, as it did when sailors steered by it and long before anyone knew what it was. The light entering your eye left it more than 4 years ago, and it crossed the same vast gap we have spent this whole journey trying to understand. What has changed is only how we see it. At the start it looked like the obvious first step beyond the sun, near and inviting, almost within reach. Now we know the truer shape of that nearness, how the small number 4 hides a gulf so wide our fastest machines would need tens of thousands of years to cross it, how the energy and the engines and the human frailty all rise up between us and that gentle light. The star has not grown more distant. We have simply learned to feel the distance honestly, and yet the wonder does not diminish. If anything, it deepens. There is something almost beautiful in a thing so close and so unreachable. A star you can see with your own eyes, allowed by every law of physics, and still beyond all practical reach. Alpha Centauri sits at that strange and quiet border, the permitted and the impossible meeting in a single point of light. It is near enough to dream of and far enough to humble every dream, and both of those are true at once. Perhaps one day, in a future longer from now than all our history reaches into the past, some descendant of ours will command the energy and the patience to send something across that gap, and the nearest star will become the first that humanity ever truly touched. Perhaps it will remain forever out of reach, watched but never visited, a light we learn to understand completely and never cross to. We cannot know which, and there is honesty in admitting it. The future of that reaching is not ours to see. What we can do is look. On the next clear night, far enough south, you can find those 2 bright points low near the Southern Cross and know what you're seeing. Not just a star, but the nearest other sun, with worlds of its own, sitting at the edge of everything we can presently do. You're looking at the closest door in the galaxy, and at the same time at a distance that may hold it shut for longer than our civilization will last. So we end where we began, with the light still waiting in the southern sky. It has been crossing the dark toward us for 4 years and more to arrive tonight, and it asks nothing of us but to be seen. The nearest star may already be impossible to reach. It is not impossible to wonder at, and on a quiet night that wonder is enough. The steady light of a neighbour we may never visit, shining patiently across the gap that defines us.